Possibly in a couple of moments, we'll have all the participants in the room. So we hold it on for a couple of minutes more.
Good morning, everyone. Today, we have our distinguished guest, Engineer Neha Sakka, with us. I want to
Push,
introduce
are we waiting for some more
them.
participants or shall we start? I'll
Ma'am,
introduce
Engineer Neha
Neha.
Sakka is spearhead of Trust TV Awareness Oath Program, a national non-commercial initiative working on inclusive electric mobility and green technology skilling. She has led 130 plus capacity building programs across multiple Indian states, engaging 5,500 plus youth professionals and government officials, though free bilingual technical training and institutional capacity building initiatives. Her work focuses on bridging energy policy, electric mobility, technologies, and on ground implementation aligned with India's EV transition and the Sustainable Development Goals. Her contributions have received national and international recognition, introducing the Indo-German Remarkable Young Voices in Transport India and the National Excellence Education Award, facilitated by the Honorable Union Minister of Heavy Industries, Government of India. She has over 7 years of experience in the energy policy and industrial area domain with Jaipur Vidyut Vitran Nigam Limited, Energy Department, Government of Rajasthan. Today, she is going to deliver us the lesson on role of open access in power market. Over to you, ma'am.
Hello, am I audible to all? Am I audible to all?
Yes, ma'am. Yes,
All
ma'am.
right, and is my screen
Yes.
visible? My screen is visible?
Yes, ma'am. You
Okay.
could make it full screen if you want it to be.
Yeah, I would love to do that, but I think there is some glitch. Every time I do that, I
Not
get
a
out
problem.
of the
Not a problem.
meeting.
Still it is looking sufficiently visible.
Okay, thank you so much for your feedback. Good morning, everyone, and thank you so much for that warm welcome and introduction. In my lecture today, we are going to learn open access. Can someone tell me in the meeting what all do we know as a base of open access in electricity? Even if we know little about it, just itsy bitsy will do. I'm looking at the chat. You can type also. Open access market in electricity. What is it about? Accessible to all. Perfect. So when we talk about electricity, who deliver it primarily to us? It's majorly the discom of the state. Every state has got distribution companies that distribute electricity to us, taking it from the transmission companies and they take it from the generation companies. This is the flow in general. And traditionally, it has always been under the government utilities that they deliver power to you. And we have to buy it from them. So, what Discoms does for us is they get electricity from whatever sources, wherever they want to, they like to, they find it suitable for them or for us, they judge it and deliver it to our home. And what we do is we pay them bill or the charges or the money in return of that electricity. Yes, so many people answering. Thank you so much. So here, what we have is we have no choices, no options, or no brain to even apply that from where are we getting our electricity. Open access gives us this liberty, the freedom to choose the sources of the energy. However, we cannot leave the DISCOM entirely out of the context because it's their infra through which that electricity comes to us. So we use DISCOM merely as a means to distribute that electricity or to fetch the electricity for us. But from where will we get the electricity? That's our decision. We decide it. And same is for transmission utility. Whatever the big lines are there, for example, 132 kV lines or 220 kV lines, these and their role just stayed limited to transferring the electricity, same as DISCOM. Right now also, transmission utility only decides the transmission charges and all. They have nothing to do with what kind of sources we are using to deliver electricity. They do it for the DISCOM. DISCOMs chooses from where to buy. Transmission utility transmit that electricity without any if and buts, and DISCOMs sell it to the consumer. So what we do is here we directly connect to the point of supply to the source, and we tell them that we are going to buy electricity for you. Discom says, okay, we will buy it. We will take it for you, but you have to pay us some charges. So that is the concept of open access electricity. Today, in this, we are going to connect the dots and we are going to understand what are these regulations and policies. We will understand it in very, very simple terms. I will do my best not to use any technical jargon or industry jargon so that we can have our foundation strong. In this, we will also cover what are the kind of charges that are included in these regulations and how we can develop more research as in a research academia into this field. And now we will connect one important aspect to it, that is electric vehicle charging station. As we have seen that there are n number of guidelines and n number of policies coming up in the state and on the national scale in terms of establishing EV charging stations and to help adoption of electric vehicle. These cannot be excluded when we are talking about green energy open access or open access for that matter, because these are going to be like the biggest one of the biggest sources for consumption of electricity, and for them we need good amount of electricity and we are going to procure it through some other means than discoms. And we will see that how can we structurally predict that how much electricity would we need, or green energy would we need for the EV charging stations. Here, there was one point that I have heard from academia a lot that I want to solve through this session. That is that they do not get the point of inputs, like what are the reference point or data points to feed in their research to reach to a certain conclusion when it comes to policy and certain things like that. So there are a couple of ideas in these slides that you will get how we can use policies or regulations or petitions to draft your research models using AI or something that can process large data. So this is what we are going to cover today. Now, this question is a very, this session overall is a very case based study kind of session. So it helps us form more ideas, to come up with more ideas. Now, my question is, can anyone in India set up EV charging station? Like me, you, HOD of the institute, can anyone do that? Does anyone has liberty to do that? For example, for petrol pump establishment, we need license and a lot of permissions. Is it same for EV charging also?
आवाज तो चालू
The voice is buffering. Maybe we could use chat section. In India, can anyone establish a chain of EV charging station? Is it permissible? It's a delicensed activity in our country. So anyone, me, you, anyone for that matter, can establish EV charging infra. Now let's say that we are going to establish our charging station on a highway. We are going to establish kind of 500 kilowatt chargers, 240 into 2 at one place, and we are going to have 500 kilowatt chargers at the distance of 100 kilometer, and we will stretch it over the span of, let's say, 400 kilometers. So we will have four chargers all over, accounting to 2 megawatt of electricity. Now when we are establishing 2 megawatt of infra on the span of 400 kilometer, we will need good amount of electricity. We have two options here. Either we can procure it from Discom, 2 megawatt, or we can procure it from our own plant that is situated at some place else that produces good amount of electricity. And I can use it at somewhere else where it is required. For example, in Karnataka, EV adoption is good. So if I set up my charging station there, it might be a good investment. So I'm setting my charging station in Karnataka, but I need electricity from Rajasthan. So, which Discom will help me? Can I ask my Karnataka Discom that I don't want your power, but I want Rajasthan Discom's power? It cannot be done like that. So, what we do is that we tell the Discom that I'm establishing a plant in Rajasthan and it's my own plant and I need a power from that plant to these charging station. Or I can say that a friend of mine is establishing a plant in Rajasthan in a solar park and I need power from that. And hence, I'm not going to take power from you. So this is called open access. From there we can procure 2 megawatt of power for our charging station. Another quick question: how will we begin? Hello. Correct. For open access, we will apply to the SLDC also. We will, or we can apply directly to the DISCOM, and the wing that sees the open access section of it, they can forward you our application to SLDC. It works either way. Correct. Very nice one, Chichi. Perfect. So the question is again, how do we start? Like, if I tell you that let's sit on the table and plan establishing a chain of EV charging infra. How are we going to figure out where do we establish, and how do we start thinking, like what's our first chain of thoughts? If we have space and specification standards, perfect. We do have specification standards, but to locate the place in the entire country, what are the questions that will pop up in our head? So basic questions that we will go through is that where do I exactly set up my plant, so that my charging station, so that we get the maximum output, for example, the maximum ROI, maximum profit. So what is the exact location, which national highway, which state highway that I can locate, and I establish my charging station there. I will reap the best of it. The best footfall will be there. It could be a state highway or national highway with maximum electric trucks running on it, tractors running on it, electric buses running on it, or cities where the influx is very high. Secondly, since electricity is going to be my continuous raw material that I would use for my EV charging infrastructure, it should be cheap because it is a continuous input for a year. So in 25 years, I should get cheap electricity all throughout so that I make good amount of profit. That would be another part. And of course, when the charging station is supplied by non-renewable resources, it kills the whole foundation and the whole vision and the sense of green technology altogether. So to do this, to account take it into account that for next 25 years, how am I going to make my charging business most profitable? In this, we have to see that all throughout these 25 years, how the electricity cost is changing. I'm not talking about the discom electricity prices. I'm talking about when I'm going to draw power from my own plant that is somewhere in Rajasthan, let's say. So for all throughout the years, 25 years, how much the cost and the charges will vary that my plant bears. For example, the charges in Rajasthan today are XYZ. So in 5 years, for getting the open access electricity, what will the charges be? Will they be reduced, increased? And then next 5 years, what they will be? Reduced, increased, and that will impact my overall ROI. So that is one thing. Second thing is that how the new technologies, for example, the peer-to-peer energy market is now coming up. We have some portals being developed in Kolkata and Delhi. They are running the pilot also. How will that be impacting and getting me more revenue out of it? And vehicle to grid concept is already on. Many have developed their prototype and are trying to commercialize. That will greatly help in P2P concept, of course. Here the main component and the data points that we need is that how the charges of open access, the wheeling charges, transmission charges, additional subsidy charges or cross subsidy charges, standby charges, all those lot are being impacted. What are the factors that are impacting it? From there we can forecast that in next 25 years what will be these charges, and from that we can give one input to our charging stations forecasting, ROI forecasting. Secondly, when we can figure out from all the adoptions of EVs that where the EV adoption is increasing and where the subsidy is being given and how they are being implemented, that there will be the largest or most largest footfall in the country. These are the spot where we go with the establishment of EV charging station. So, have you ever seen a portal that do this for you? That with this portal you can simply enter your requirements, like if you want to establish 10 charging station of 500 kilowatt, or in our case we want to establish 4 charging station, we just enter the number 4 into what kind of power, like 500 kilowatt, what kind of power, open access power, and it gives us everything that established here. So you will be getting your ROI in these many years and things like that. Do we have such simplified portals that gives us all these solution at one place? Because EVs are now growing a lot, so this kind of portal will give you direct answer to all the question for the beginners at least. What do you think? Is it workable, doable? Is it a good idea? I'm waiting for the responses in chat. Okay, yes, portals are there. There is a portal by EV Yatra, that is by BEE, that gives us the charging station that we are going on the route. So from where do we charge our vehicle? That is the kind of portal we have. Do we have a portal which can tell you where to establish your charging station and where to take power from, so that you get the best ROI in 25 years or so? Okay. So this is the kind of response that we expect with the help of AI from such portals. Like, it gives you straight, clean answer that this is the place where you build your project. It gives you so and so visits a day by whatsoever year. Source your power from Rajasthan instead of Karnataka. This is the overall savings that you do in transmission charges. And it gives you the entire concept of your return on investment, from where do you get the power and where do you establish the charging station. This also includes the green energy open access or open access power. So this is what I'm talking about. Can we develop a portal that gives us straight away these answers, that you procure power from third party or bilateral or go for captive, such direct quick answers? So this is what I was talking about. For example, if we can predict the EV traffic on Indian highways using whatever government data we have, all the policies that we have, NHI portal or fleet company reports, Parivahan portal we have, and then we can predict what will be the adoption of EVs in next 25 years. Because I've been talking to many professors, even at MNIT, and they've been telling me that prediction of adoption of EVs is a very typical thing. It is not that easy as we do for other new technology adoption, because there are many things affecting it. More importantly, policies and uh, human behavior are the two major factors that cannot be directly assessed. So if this can be done, that is projection of this market, it will be great. There are many reports from Niti Aayog or CEEW or ICCT that are telling the prediction, but again, they have to be associated with policy implementation as well. So they can be used to predict the data as well. Now, when we talk about open access charges, that is the input of our charging station. These are the places that we could go to research our data inputs. For example, somebody said that we can go for tariff orders. That is perfectly fine, and that is what we do. We can go to all the regulatory documents, policies and schemes, petitions, and everything. They have all the discussions that have happened to increase or decrease the charges, all the kind of charges that are levied on open access consumer, and we can use AI ML to train them to assess that how these charges are changing and based on what factors. So these could be the factors that impact the open access prices, and then we can predict and forecast what will be the open access charges given the condition of the state's economy and the demand and the rise of solar consumption or renewable energy consumption. These are easily available on State Electricity Regulatory Commission. This question was asked to me by a student in MNIT only, and hence I have put this in place. That we can predict open access charges, but it is going to be a very tedious task. But AI ML can make it really uh, doable for us. Then this is the idea that is working on, that is being worked upon. Sieve has developed this portal wherein you can enter the state from where you want electricity, and you can enter the state from at which place you're going to draw the electricity through open access, and it will give you the entire costing of it, that how much per unit energy is going to cost you, what will you save in a whole year, and things like that. But it does not forecast the electricity, it tells you the savings in electricity. So my idea is that if we can forecast open access charges and EV adoption, we can actually figure out that at what places we can develop our charging station for the maximum benefit. We can also consider a portal wherein we can have farmers joining our hands and developing solar stations or solar plants at their farms in terms of agrovoltaics, and then we can use those plants as our plants, giving them the rent for our charging station. That is also example of open access. So it is this is how we go about thinking that what open access can do for us. These are the places from where we can get the inputs for our forecasting and train our AI models. So for example, for Rajasthan, approval of ARR and tariff for year 25-26 this you can get on RERC website, and you can download it. And that you will see n number of discussion going on. For every charges there is a whole lot of discussion. So the behavior could be derived to train our models, and from that we can predict what will be the next era of charges. If you want a screenshot, we can work this upon together. I really like this idea. This is the tariff for supply, and here we have TOD rebates. Another point to keep in mind when we talk about open access power drawal, because we cannot draw power during peak hours. So these are the small points that will help us predict our power cost when we are going for open access power drawal. This is ordered by Jaipur Discom. As you can see, during the peak hours, 6 to 10 a.m. early in the morning, there is surcharge of 7.5 rupees. This order is of 2024. Right now in 2026, we have entire different concept of peak hours depending upon the sorry, in 2023 it was majorly about off peak hours and peak hours in terms of morning and daytime, but in 2024 we have changed it to solar hour basis of peak hours and off peak hours. So here you see that as the TOD has changed, we can see the similar changes in other charges as well, and we can predict that on basis of what will the charges change in future. This was changed because we had excess solar, we started having excess solar with implementation of kusum and everything. So we have to shift the entire concept of TOD on the basis of availability of the solar rather than the consumption behavior of the user. So you will notice that 12 p.m. to 4 p.m. is the time where we have abundant solar energy, and the excess solar is there in the electricity grid. So there we are giving rebate of 10% so that users use electricity in that area of time. And then in morning peak hour and evening peak hour, in these hours there is no solar available or renewable in majorly solar available, so we are surcharging them so that they don't use it in that area. So this is how the behavior the TOD rebate change. So this was one of the example we can train our AI model on. Again, another point is that how we can include new technologies like vehicle to grid. Once a vehicle to grid is approved commercially, and we included it in our regulations. For example, Kerala has released their draft regulation on it, that how do you go about vehicle to grid connecting to P2P trading business. So once we do this, our vehicle charging station will not be only for vehicle charging, it will become a pool of electricity from where we can sell our electricity to maybe a nearby home or a complex, or to maybe a farmer. So it's going to be an entire delicensed process of who is going to sell electricity to whom. Anyone can sell electricity to whom. I'm very much sure that you must be aware about P2P trading business, and I'm sure that vehicle to grid is your expertise. So I'll leave it to that. But these could also be considered when we are doing the research and the impact of these. And again, the sources are Central Electricity Regulatory Commission and State Electricity Regulatory Commissions. The models, if you want to refer to, we have Delhi and Kerala doing great job on this. And of course, we have Unified Energy Interface coming up. So that is going to solve a hell lot of things for us. So another strong point to consider. Now we are getting to open access part. So that was the major application of open access so far that we will have in bigger chunks. So you can replace EV charging station by big industries as well. But that was the concept to tell, because with EV charging, we have a lot of different concepts associated with it. So I took that example to make it more clear. In Rajasthan, there are 3 discoms. Depending upon the geography of the state, we have divided it into 3 parts. Similarly, it goes for entire country. Electricity is a state matter, so every state is divided into different discom that delivers electricity to particular consumer individually. So now let's say that our charger is located at Pali, Jaipur, and Ajmer. Here, when we talk about 3 different discoms having our charging station, because we will be building it on some highway, my charging station and drawal point comes under different discoms and different utility. So when I'm talking about paying bill to the state or electricity department, do I have to pay 3 different bills to 3 different person, 3 different discoms? Do I have to get? Okay, that's a strict no. Yes, we don't have to, because electricity is a state matter, not a discom level matter. And also open access charges are for entire state, so you can have plant anywhere in Jaisalmer maybe, and can consume it in 3 different discom at different places. So captive plant in Jaisalmer, my own plant that's captive, that's in Jaisalmer, and 3 different locations I can have my EV charging infra, and there I can consume, and I have to pay charges that is same for entire state, that is called open access charges. For example, we are setting up our charging station on highway, let's say around the boundary of Sikar, Jaipur. It involves a lot of places, Alwar as well. So what we do is that we go and tie up with farmers and ask for agrivoltaics, that we set up the plant above your cultivation, and we draw the power from that plant is our, we pay them the monthly or yearly rent for the land, and we power our charging station on highway. This reduces our transmission losses as well and distribution losses as well. This is good for us. If we are able to develop this in periphery of 5 or 6 kilometers, that is doable in highway area. We have to definitely go for better locations. So this is one of the ideas, and we can give them complementary services like charging their tractors or trucks for loading and unloading. So when we do this, this makes us get land at a cheaper rate. Also, this helps us in um, reducing our losses. Transmission charges and the wheeling charges are still there, but losses are reduced. So the same then can be used for n number of processes. We can also install BESS for this, because when we install BESS through open access and we draw the power, we have a lot of rebates on transmission charges and wheeling charges. If we install 5% of the 5% of the entire consumption in terms of BESS, we get rebate on transmission and wheeling charges. So with each agreement in installation of BESS, we get more and more rebate on transmission and wheeling charges. For example, if our power is 100 kilowatt and we installed BESS of 30 kilowatt, we will get entire 100% rebate on transmission and wheeling charges. So this is how they are supporting BESS as well. This we have covered. Now let's talk about in detail about the open access procurement. We have seen a lot about this. One point that we will have to make clear, that when we talk about open access, earlier the rule was that if we need open access, we need to have our demand load demand at least 1 megawatt. But now, with green energy open access introduction, that limit has gone down to 100 kilowatt. And that is when you are buying power from your friend or any other third party, and it's not your own plant. But let's say that if it is your own plant, then you don't have to even go for 100 kilowatt, you can go for 50 kilowatt as well. So for captive plants, that limit is also removed. It's a very good thing that 100 kilowatt need not be at same location. You can have 10 kilowatt at certain location, 50 kilowatt at certain location, and remaining 40 at certain other location in the same electricity division. The only condition is that your bill should not be due with the discom or any other utility for more than 2 months. That's it. Now, here they have restricted this for one place as an open access also and green open access also. That if you are a single point consumer, for example, if you are taking electricity and you are supplying it to n number of consumer, for example, a colony or something, you cannot take open access because then you get the cheapest energy and then you sell it on a higher rate to other electricity consumer, which is wrong. So that's not allowed. So the people that are involved in this entire process is open access consumer that we have seen, that's us, distribution company that gets the electricity from the sources via transmission utility. We have transmission utility to get the sources from power from the source to the discom. SLDC, their work majorly is that they manages the power all the seconds of the day. They look at it very seriously, that how much power is being consumed and how much power is being generated and transmitted properly. So that's their part to manage, because if there is a lot of power in the grid and it is not being drawn, there are changes in the grid, frequency goes up. And if there is no power in the grid and there is a lot of demand, and then there are again changes in the grid, frequency goes down, and our entire frequency is built to operate on 50 hertz. So to manage all that, we have a nodal agency, and that is called state load dispatch center. And similarly, we also have regional and national load dispatch center. So if you do anything with the frequency part, that you do not generate more and consume more, but you generate less and you consume more, generate more and consume less, anyhow you disturb the frequency, they give you DSM charges. But these charges are little typical, because if you help this frequency of the system, for example, at certain day you drew more power and the frequency of the grid was high because other consumer did not consume the power, then you supported the grid's frequency, in that case they are going to reward you. But at certain day you drew more power and there was already less power available in the grid, that's your luck, and in that case they are going to penalize you. So it works on case to case basis. So they are going to charge you for that. Other charges involves transmission charges for transmitting the power and distribution charges for distributing the power to you. Generator is the person who generate electricity for you. It could be you or your friend or anyone else. Power trader is a person in between who makes sure that you get the power. For example, if you're going to have short-term power for 15 minutes or 30 minutes, you cannot go around and search for power producer for every 30 minutes the other day. So you hire a broker or an agent that do this for you. It's a hectic task, so it's better to hire them. Otherwise, if you have proficiency in it, you can completely eliminate them. But they then charge some amount of money for that. Power exchange, IEX or Hindustan Power Exchange, these are the places for stock exchange of power where you can go for short term or spot power procurement, and they discover price basis on the market of electricity that's going on with them. So they are basically the stock exchange for electricity. State electricity regulatory commission are the people who makes the regulation for us. So every state has got their own electricity regulatory commission. They may or may not agree to the single phenomenal regulation. It's there to decide what they want to do with their charges. For example, Maharashtra's open access charges are higher than ours, so we cannot tell them, or no one can tell them anything. It's theirs to decide. Similarly, that goes for us. Now, bilateral agreement is one way, third party is one way, open access, captive is another way. In bilateral, what you do is that you buy from a power from a generator. It's that simple. It's the difference between bilateral and third party is the same case that you buy power from generator. The difference is that bilateral is more of um, it's it's more of uh, how should I say, it's um, more of flexible kind of thing, where you can you can buy power and negotiate it with them, like you don't want it, you want that, you can have terms and conditions with them. But in third party, what happens is that this is my power plant, it is going to sell you electricity for 5 rupees per unit, whether you buy it or not, it's the end of the deal. With bilateral open access, you can have a open conversation that I'm not going to buy with this, let me buy with that, or these are your responsibilities, these are my responsibilities. You can negotiate on a lot of terms, like if there's a power outage, how am I going to deal with it. In third party open access, it's very straight in your face that these are the terms and condition, if you want to buy it, buy, else leave. So you have to decide it in on your own case, how does it work for you. IEX is basically used for short-term open access, unlike bilateral, it's for long-term only in 15 years or 25 years of contract. IEX is basically for short term, like for 15 days or 30 days or 1 hour or 2 hours. Someday you need extra power so for some place. And this cases, SLDC, Discom, IEX, you and your power traders, all of them are involved and you pay price to all of them. Captive generation is your own power plant and it is defined like if you and some other entity is a part of a power plant, then you should at least own 26% of the equity, and you should have to consume 51% of the electricity that is being generated from that plant. Then only that plant will be called captive. We cannot have partnership with someone else and invest only a little amount of money because we don't have money to invest it and then call it ours. With investment from 2 to 3 people, we need to have 26% of equity in that, and that is the basic place where most of the captive or group captive fails because they do not go by this consumption of 50%, 51% of electricity. Captive gives you a lot of rebate because you're exempted from crop subsidy subcharges. So if you're considered captive, you get exemption from these rebates, from these charges. And of course, this is used for long term in general. And there are wheeling charges that you pay for this section. There are other charges as well, standby charges and all. I'll give you an Excel sheet for that. Third party is something that we have discussed already. It is more like as bilateral agreement. The process and everything is same. The terms and condition are little different in this case. This is a clear differentiation between the two because this creates confusion in general. So I have differentiated in a very clear form. What are the exact charges involved in open access? As I have mentioned, there are many. The energy charges, these are the charges that you pay to the generating company. For example, somebody is selling you at the rate of 2 rupees or 3 rupees per unit, that you pay to the generator of the power station. It could be your friend, and if you are the owner of it, you don't pay anything. So you pay some amount to the generator, to your friend, and then you pay amount to the scheduling and system operating people, that is load dispatch center, state load dispatch center, RSLDC, or national load dispatch center. Transmission charges and wheeling charges are paid to transmission utility and discom utility because they are giving you their infra to transmit all the power that you require. Transmission losses and wheeling losses are kind of the losses that they consider where your power is being transmitted from one place to another. So in general, they take it as 3% or so because there. So what we that when you have access of electricity, when you have excess of electricity and you don't use it, so it is stored with discom, and then you take it at night or wherever you need it an extra drawel, and that part when you use the stored electricity they charge you some percentage of it, let's say 11% or 8% of it. For example, if you have 100 units, they will charge you 8 units for storing it with them, and then you can use the rest of them. It has got entire different concept. We can take another day to go through it. It's a very interesting topic. So these are the banking charges you pay to the discom. Carbon tax applicable in some state and waived off in some state, depend state wise. Cross subsidy charges, it is to compensate to the discom because uh, there are so many subsidized users of electricity, and it is through the big users that discom earns and subsidize them. Now that the big users are going away, discom has to be compensated, so that is cross subsidy surcharges. Additional surcharge is because that when you contracted with discoms to buy power from them, they constructed entire infrastructure for you. They procure power for 25 years from someplace else to deliver your demand, but now that you are going away, they need some charges to fix all that, so that is additional charges. Parallel operating charges and grid support charges, these are the charges that we have to pay to discom in case where our plant is not working or anything happens. Discom is always there to give us the power. Our plant will not stop. We always have discom to support us. So for that, and by default infrastructure, by default support availability and proper power delivery, we have parallel operating charges and grid support charges. Standby charges and one-time application fee and security deposit are when you deposit your application. For example, someone brought up that we submit our application to state load dispatch center, so these are their charges that we go through. So this is how the entire lending cost looks like. We have one-time cost, that is the application fees and security deposit. This is only for open access. If you are third party bilateral or ix or anything like that, if you're establishing your own plant, one-time cost will also include capital cost and investment cost of the entire plant. Monthly fixed costs are transmission charges and wheeling charges. These are based on the capacity. These are charged on per kW or kVA basis. It has nothing to do with whether we use electricity or not. If we have solar plant there and we have
Excuse me,
is someone speaking?
your slide is not visible.
Oh, I'm sorry. uh is it okay now? Is this visible right now? Is this visible right now?
Not yet.
Not yet. Can we buy green power directly from Discom? Just 1 second. No, we just have to do a tri-party agreement. Okay. Yes, we can buy green electricity from Discom. They
It
give
is
us a
visible now.
certificate.
Thank you.
Okay. Um, was it not visible
The
from a
slides
long
are
time?
visible now.
Was it not visible from a long time? Okay, so somebody brought up tri-party agreement as well. Yes, that works when we are going for bilateral or third-party power procurement. We do have tri-party agreement because there is one another party involved in giving us the power. So when we are developing our captive power plant, we don't need a tri-party agreement or via that. And I missed the no on what this what part that no is for. If you could please elaborate, we can take that up. So this is majorly the entire cost that we will be bearing for our open access procurement. Application fees, as already discussed. Now, the point that I wanted to highlight is monthly fixed cost. This is when whether or not we use power or energy, if our factory is lying shut for a month or so, if there's no EV footfall at our stations for a month or so, we still have to pay transmission and wheeling charges to Discom. It is regardless of our energy consumption. So this is one cost. Another cost is monthly variable cost factor, that is energy charges from the generator. It could be bilateral, third party, IEX, anyone for that matter, if it is not a captive plant. So whatever consumption we do or power drawal we do, we pay to the generator. energy charges, per unit energy charges. Then we have SLDC and RLDC charges. We pay them for the entire consumption and drawal amount of unit. Cross subsidy surcharges, additional surcharges, electricity duty, these are on the basis of our energy consumption. GST on services, again, it is nil. It will not reflect on the bills, but the services are taxable. We have banking charges. This is for when we um, avail the provision of banking. If there is no banking, then no charges, of course. These is for banked energy. Standby, if we are using, and DSM charges, that is deviation settlement mechanism charges. If you please do focus that there is a plus minus on it. So if we support the grid at times of deviation, we get paid for it. If we worsen the condition of grid at times of deviation, we are billed for it. So this is how it works. Overall, these are the charges that are included. Again, there are urban charges, water conservation charges. These are basically paid to government directly, just like electricity duty, for example, and they do not impact much on our consumption. So I've not included that. These are the major costs that goes in. This is a good portal that you can explore, Crane Open Access. It gives you a lot about the entire procedure and all the agreements and everything. It defines things very clearly for a beginner. So if you want to begin and are looking for a start, this is a good point to begin with. This is the cost breakdown of what exactly are we paying. For example, for long-term agreement, we have to pay 1 lakh rupees, medium term 20,000, and STOA for short term, we have to pay 5,000 rupees. This has nothing to do with per kilowatt or your the amount of energy you will be drawing or the size of the plant. This is straight away depending upon the time duration, and for that you pay this amount. And then there are other costs. For example, bank guarantee, this is refundable. So once you uh, set up the plant and everything happens, you can get that back. Security deposit, again, this is to cover all the for it's kind of cover, it kind of equates to 3 months of all the estimated charges. So security deposit barely equals to 3 months of SLDC charges or transmission charges, wheeling and cross subsidy and additional charges. So at different to different people you pay different amount. SLDC, RVPN, that is the transmission utility of the state, and to the discom, wherever your discom is. It could be in Ajmer, Jodhpur, or Jaipur majorly. Yeah, so that bank guarantee is on per megawatt scale. So if your plant is 5 megawatt, we pay 50,000 rupees for that. It is not on one like, it is not irrespective of the capacity. I have broken down all these details into an Excel sheet that I'll show at the end of the slides. And from there, you can go about and play with it and do more research and improve these things. And I really support using ML in any way that can be used to predict the surcharges. It will help discoms as well. Here you can see there are parallel operation charges mentioned, and there are terms and conditions where they will be applicable and where they will not be. Additional surcharges, 0.72 rupees per unit that is paid to discom. We have for different category consumption, we have cross subsidy surcharges. However, they are same for all of them. At transmission level, we have different charges for different voltage level. For 132, that is a EHT, high tension service, we have only 1 paisa, and then for different voltage level we have different charges. Now we can go for tariff orders or petitions and the regulations for entire 10 years or 15 years to see how these charges changed and what are the probable scenarios in which these charges will change in coming years. So this is the concept of how the banking is done and what are the conditions and the process for that. Since time won't permit us, I will leave you with this to explore, and maybe if we have some interested candidates in it, we can have one-on-one discussion for this. But one thing that you should see is that in green energy open access, if your contract demand is up to 100%, then the caping is different. And if your contract demand is more than 100 to 200%, the capping is different. This is to say that if the plant is 100 kilowatt and consumption is of 100 kilowatt, and in case plant is 200 kilowatt and consumption is 100 kilowatt only, then the bank energy capping is different for both the cases. This is what I meant to say. Also, when the energy is banked and you're not using it and the cycle elapses, so for that elapsed energy, though you will not get the energy, but you will get the renewable energy certificate for that one. So this is one of the good things that I found. To get the adoption rate and the probable cities where the EV charging station would be blooming, you can refer to these guidelines, because in these guidelines they have mentioned what are the priority cities, what are the priority state highways or national highways. You can definitely go in that and check that what are the probable places where the EV charging station would be there. This was to explain the entire ecosystem of how the land cost of EV charging station with government is being taken up, and what are the requirements for EV chargers and the area requirement, and hence the power requirement. They also mention the charging fee for the consumer based upon the off peak and peak hours. What are the service charges that you can pull on the consumer, unlike before where it was very much monopoly kind of thing. And they have this common confusion in electricity tariff that the category of EV tariff, that is 6 rupees per unit, is applicable to EV chargers. It is not applicable to EV users, it is applicable to EV stations. Now these are the points that I added by collecting from interviewing people what they do not understand in research and academia, and hence I have included in this one. So the point is to tell you that from these guidelines we can actually figure out कि कहाँ पर हमारे EV के zones बनने वाले हैं. उस हिसाब से हम predict कर सकते हैं कि अगर हम यहाँ पर EV charging station लगाते हैं and we use some portal like Seed ने जो develop किया हुआ है और procure हम open access के through इन जगहों से करते हैं, तो हमारा जो total cost है या total penetration है वो कैसे land होने वाला है. Again, charging station as a solar carport, another good idea, because aane wale time mein we will not be staying till 240 or 250 or 300 kilowatt of chargers. We are going into megawatt charging now. So these are the points that we can go for. पीएम ई ड्राइव के अंदर दिस पॉलिसी इज ब्रिलियंट. इसमें बहुत ज़्यादा सब्सिडी दी हुई है. दे हैव इनफैक्ट लिस्टेड आउट कि कौन से 20 हाईवे उन्होंने प्रायोरिटाइज किए हुए हैं और कहाँ पर चार्जर्स लगने की संभावना बहुत ज़्यादा है. सो दीज आर द पॉइंट्स दैट वी कैन यूज एज एन इनपुट एंड ट्रेनिंग मॉडल टू AIML, एंड देन वी कैन फिगर आउट कि हमें कैसे कॉस्ट लैंडिंग निकालनी है. अगेन उन्होंने सिटीज़ का भी बताया हुआ है. सेम इज़ फॉर PM ई-बस सेवा एज वेल. So we can use, in fact, guideline also to do our predictions, these schemes and the guidelines. These are the minimum power requirement for chargers to be set up. These chargers are heavily subsidized. In fact, इनका infrastructure भी heavily subsidized है. अगर 20 लाख का भी लगता है तो they have given their benchmark कि हम 100% में इतना इसको पूरा subsidize कर देंगे. So if it is transformer or the cables or anything that for that matter, that including the EV chargers and the land and everything, that is 100% subsidized. तो जो हमने अभी cities देखी थी वहाँ पर बहुत ज़्यादा पेनिट्रेशन होने का स्कोप है. सो दीज आर द प्लेसेस, वहाँ हम ओपन एक्सेस से पावर ड्रॉ करके कैसे हमारी पूरी लैंडिंग कॉस्ट कम कर सकते हैं, दैट इज़ अ पॉइंट टू बी एक्सप्लोर्ड. These are the scope and relationship between various kind of business model people in India. बहुत सारी entities इसके अंदर जुड़ी हुई रहती हैं. There is मल्टीपल एंटिटी बिजनेस, आई वुड से. इतना कॉम्प्लेक्स और कोई बिजनेस नहीं है और इतना इजीली एक्सेसिबल भी और कोई बिजनेस अभी नहीं रेडी हुआ इंडिया में जो इतना ज़्यादा सपोर्टेड हो गवर्नमेंट से. लैंड इज सपोर्टेड, वी हैव chargers cost being supported, infra being supported, and here when you have EMSP and CMS models with you, things are very easy for us. For example, charge point operator अगर किसी CMS या EMSP developer से contract करता है या खुद का भी बना लेता है, and he establishes a charging station in under PME drive, तो उसको किसी चीज का कॉस्ट डायरेक्टली बियर करने का नीड नहीं है. सो दिस इज अ वेरी ग्रेट pathway that we have. Renewable energy based इसको सपोर्ट करते हुए when we go about, there is a lot of requirement of research in this field. जब हम renewable energy based इसको सपोर्ट करते हुए आगे जाते हैं, सिर्फ ग्रिड पर इम्पैक्ट की बात नहीं है, इट्स ऑल्सो अबाउट मार्केट कि हम मार्केट में कैसे एंटर कर रहे हैं विद गुड ROI. सो दैट इज वेयर आई थिंक दैट आप लोगों के इनपुट्स बहुत हेल्पफुल रहेंगे. जब हम EVSE और सॉफ्टवेयर की बात करते हैं, तो चार्जिंग स्टेशन के लिए जब हम EVSE यूज़ करते हैं, उसके अंदर हमें एक चीज़ बहुत अच्छे से ध्यान रखनी पड़ती है कि वो OCPP कंप्लायंट हो, और ये कि जब हम ऐप्स का यूज़ करें वो OCPI कंप्लायंट हो, ताकि वो सब लोग आपस में कम्युनिकेट कर पाए कॉमन प्रोटोकॉल पे. हाउएवर ये सारा मैटर जो इंटरऑपरेटिबिलिटी का है, दैट इज गोइंग टू बी सॉल्व बाय यूनिफाइड एनर्जी इंटरफेस. उसके अंदर हमारा चार्जिंग स्टेशन में व्हीकल का कनेक्टिविटी, चार्जिंग स्टेशन का ग्रिड से कनेक्टिविटी, उसका बिलिंग होना, पीयर टू पीयर में ट्रेडिंग करना, ये एक बहुत बड़े अम्ब्रेला के अंदर आ जाता है UEI में, इंक्लूडिंग ओपन एक्सेस एज वेल. सो विद दिस आई वांटेड टू शो दैट हमारा जो हमेशा से एकेडेमिया और इंडस्ट्री में गैप रहा है, एंड वी हैव ऑलवेज सेड कि हमें एकेडेमिया और इंडस्ट्री को साथ लेकर चलना है. आई वुड एड वन मोर लेग टू द system, that is policy. Academia, policy and industry, these are the 3 points that goes together. Academia में जो research होता है वो policy में directly reflect करना चाहिए, so that policy उस according बन सके कि हमारी country जा किधर रही है. पॉलिसी जब भी इम्प्लीमेंट होती है तो अकेडेमिया में वो सारे पॉइंट्स होने चाहिए रिसर्च में, कि पॉलिसी अगर ऐसे ऐसे बदली है और ऐसे ग्रो किया है, तो वो रिसर्च इस तरह से हो कि वो वापस से लूप को कंप्लीट करते हुए पॉलिसी में सपोर्ट करे. एंड देन जब कोई भी मार्केट या MSME या कोई भी इंडस्ट्री फ्लरिश करती है, तो उसमें पॉलिसी का बहुत बड़ा रोल होता है. एंड देन एनी टेक्नोलॉजी can flourish in industry when these two work together. As industry flourishes, we have more scope of improvement, and then again research, then again we find loopholes in the policy as well, and it helps us improve academia and policy. So well, under this umbrella I wanted to cover open access and EV charging station. So I hope that it was an overall explanation, building a foundation for you. I had to take this up in a very quick manner because this lecture was designed for 2 hours, discussing a lot of points, but I have compressed it into 1 hour. So I'm very much hoping that there were a lot of points that you got, a lot of questions, a lot of disagreement and agreements that I'm ready to discuss. Thank you so much.
Thank you, Neha ma'am, for the enlightening lecture and really bringing in the industry perspective. Dr. Satish, I hope I'm audible.
Yes, sir.
I think out of all the lectures that we were having over this FDP, this one was special and interesting for all stakeholders, because we bring what is happening in the industry, and that is what brings value to the academia and the researchers who are relatively less in touch with what are the current practices and what are the practical challenges and practical new evolution that are happening in the industry. So thank you, Neha, for this program and sparing your time for this. Thank you very much. We hope to see you in some other event as well.
Yeah, sure. And I can share the Excel sheet if anyone is going to work on this, if at all. It was very much delightful being with you. And this Excel sheet, in a couple of minutes, I'll explain if someone is interested. There is entire, I would say, holy book of open access charges. What charges are paid to whom and why they are paid? What are the charges? What are the entities involved? And also the exemptions that are available on the basis of from where you are drawing the power and how you are drawing the power. If anyone is doing some research on it, I'm very much happy to share this to support your work. Thank you so much.
I think that would be really interesting. Even if you quickly help us to go through it. Presently, the font size is slightly small, but just help us focus on that.
Yeah, because it's a technical glitch. Every time I do it in full size screen or something, I get exited from the meeting. I didn't want to risk that. So I'm so sorry about it. And thank you for understanding that.
Yes.
And Rohit sir is here, my senior, and of course, a very brilliant person. Sir, how did I do? Do I need to improve? Where do I improve?
I think we in academia we always appreciate what comes from the industry, because unfortunately, being in industry, you are able to catch up with what is happening, and being in academia, we are unable to do that. So it's always a learning curve for us when we are talking with the industry people. We always enjoy that. There is always something to learn, and that is what makes our academic programs strong. So
Ah,
it's we always cherish those.
oh, thank you so much.
Yeah. So I think if you can share that Excel sheet, so I will put that in my classroom so that all the participants can have it, and if they have some doubts, they can directly email you. So that is fine.
Yes, yes. I'm just trying to get it done. It's not showing in the window section. Maybe it's network issue. I'll share it on mail if that's okay.
Yeah, yeah, that is fine. That is fine. Like you can
Okay.
share it on email, and then I will put it
Hmm.
on the share with the participants.
All right. So, and I humbly request all of you, all the participants, that please do share your questions with me. The slides that you have seen, it's not a topic oriented slide, it's FAQs oriented slide. I have talked to academia people and I have designed their question in form of lecture. So, I humbly request all of you to give your questions so that I can add those questions as a topic in my lecture. It helps a lot of students and faculties. Thank you so much for having me.
Thank you. Thank you, Neil.
Thank you.
So, sir, I think we can have our next lecture, right? So you are not audible. You are muted.
Oh, sorry. Just give me a moment. I'll rejoin again in 1 minute.
Yeah, fine. Thank you.
Then I'll join. Dr. Satish, I hope I'm audible.
Yes, sir.
Okay. So I think I'm supposed to give a presentation on smart grids.
Yes.
Yeah. I'll take a different view of how I'll take a broader view or an overarching view of what smart grids. I think the slides are visible as well as I'm able to
Sir.
move them as well.
Yes.
So thank you. Though I understand that there are less number of audience today, I'm not sure why, but still I'll try to make the best out of it. What today I'll be focusing upon is overview of what smart grids is and trying to understand exactly because there are different perspectives of smart grid. So exactly when we talk about smart grids, it's just an introductory lecture on what smart grid means for different people, so that when a person, the storyline doesn't become similar to that of an elephant, and few blind people who have their own sense of what an elephant would look like. Same is the storyline with smart grids over the last decade or so. People have started, people have their own versions of what smart grid would mean. So I'll just try to take you through what.
आपको आवाज कर रहा हूँ.
Hope I'm audible, Dr. Satish. Okay, thank you. So just giving you brief definitions, what are the key drivers for smart grids? What is the broader conceptual framework for smart grids? And what are the intricacies and where is the Indian scenario heading towards? These are the 5 key points that I'll be talking about. Definitions, the drivers for smart grids, conceptual thought process, the intricate architecture, and thereafter talking about what is the state of affairs in India. So broadly, we all have been talking about smart grids in terms of smart generation, smart transmission, distribution, control. They're on taking a wider view of wider integration of these verticals, being able to observe different parameters in these systems with a depth, and also being able to control those components from remote locations in a coordinated fashion is what a smart grid would look like. So as far as when we use the term smart grid, essentially we differentiate it from a regular grid in a way that a regular grid would not have those features which allow two-way power flow. That is one part. And apart from that, it would also not allow that much of coordinated observation and control in the system. To make this all workable, we have to also implement a lot of information technologies. We have to, I would say, implant information technologies at different levels in the system, different layers in the system, so that all information at different layers is captured at certain level and processed so that visibility or observability in the system can be created. This is all the more essential for allowing the customers and even small stakeholders connected at faraway nodes to participate, because unless and until they are connected to the grid, unless and until they are visible, and also consumers themselves are able to see what the grid is doing or how the grid is behaving, it becomes difficult for the consumers connected to the grid to interact with the grid, as well as for the grid to see what the consumers are doing. So in order to enable the stakeholders on either side to see each other's behavior, understand how they would behave, and accordingly plan for the future, how to go about plan for the future operation and planning. Then only the real benefit of that investment in terms of IT comes in, and then only we can broadly call it a smart grid system. Obviously, this would involve a lot of communication technologies, investment in communication technology, investment in IT, so that whatever communication, whatever information we are compiling, the data that we are compiling, we are able to process it and appropriate decision-making tools in the system. This requires, obviously, as discussed, this requires a lot of sensors at different points, different nodes. It could be transformers, it could be transmission lines, it could be consumer premises, it could be components, devices working in the consumer premises. The consumers could be industrial or residential, commercial. So wherever we are able to put up those sensors, which may have an impact on electricity consumption, which may have an impact on the power flow in the system or in the generation, sensors being put up in transformers, sensors being put up in different parts of the power plants. They help us to understand exactly what are the values of the parameters, and they can help us to accordingly take a judgment on whether those are functional or not, whether those are crossing the limits, or how do we coordinate the function of the different components in the system. Obviously, this is because now we have got more and more interconnections in the system. So in an interconnected system, the sensors which we are able to get information, we are able to automate the system using IT technologies. The benefits that we draw from this, we all understand broadly as electrical engineers, we understand that it would improve the quality, reliability. It creates opportunities for new products, services in the markets. Obviously, it increases the customer choices because the customer, based upon the information available, is able to make informed decisions about when and how much and what type of electricity products to be consumed. Automation communication obviously is an integral part, provides opportunity for larger RE penetration, larger RE integration, DR integration, and storage in terms of electric vehicles or other batteries, energy storage mechanisms. Creates opportunities for the demand side for demand response, ancillary services, and ability for the grid to operate in a microgrid fashion. So all these facets, they are advantages that the smart grids offers, and thereafter many policymakers, investors, they are focusing on making the grid smarter, which can really encourage the customers, the consumers to be a part to interact with the stakeholders. Now, broadly speaking, there are a lot of things that are happening in the grid at the higher level. Earlier, the visibility and the simulation side of the grid was relatively weak. As a system operator, the ability to see even the larger parts of the system, what is the quantum of generation, what is the power flow, what are the loads at different nodes, that was limited to certain control rooms, control centers, which had a visibility at the local level itself. However, visibility at the higher scale, at the national level or at a very high scale at the grid level, was relatively limited, and the ability to foresee the impact of disturbances or changes in certain parameters on rest of the system operation was limited. that essentially has led to more and more investment on real-time simulations, so that the changes can be sensed, the changes can be based upon the changes, the behavior of the grid can be prejudged, and accordingly decisions can be taken to operate the grid in a reliable way, focusing on the wide area reliability. That also, apart from that, a lot of focus has over the period has been into the area of network optimization, because a lot of investment and grid congestion is happening. A lot of investment is required to operate the grid. Along with that, on the customer side also, customer participation is an important factor that needs to be brought in. And that requires a lot of investment on the customer side in terms of advanced metering infrastructure. Um, um, Along with those, more market solutions also need to be brought in. And those market solutions obviously require communication between different nodes, as well as obviously new business models that we can touch upon in some other class. One of the basic features of these smart grids is that power flow, which was earlier restricted in a unidirectional way from generating plants, to be stepped up over the transmission system, to be stepped down on the distribution side, and thereafter being consumed by the consumers. That concept is slowly changing away, with more and more integration of RE on the customer side, with more and more storage facilities being developed on the distribution side. That creates opportunities for the customers to generate and consume power, as well as to inject residual power into the grid when the consumption is not so high. So that leads to reverse power flow, and that power may be used by some other consumers at some other node in the system. So eventually it creates opportunities, it creates scenarios of reverse power flow. So all this system has now to be redesigned to ensure that reverse power flow or bidirectional power flow is enabled. The system protections, they do not get activated in terms of reverse power flow. That is one segment. Apart from that, bidirectional flow of information is equally important. It is not only that information has to be compiled from either the generation side or the consumer side. Not only the present day control room operators have to compile information, they also have to pass on control signals. So rather than the control person only seeing information, maybe it may be that of plant, it may be that of network, or network for transmission distribution owners, or on the retail side, possibly for the distribution network operator or the retailer looking into the information of the customers. It is not only about looking into that information, but again passing on control signals so that the systems can be operated remotely. So nowadays we have got more and more power plants being operated, I would not say remotely, but the man on the field is relatively limited. Though the major changes that are happening, they are happening on the transmission and distribution side, in which remote substations are coming up in a big way, specifically in power grid side. A lot of remote substations are coming up in which they are manless, and the whole of control and communication is being done by people sitting at faraway control rooms. So that requires bidirectional flow of information. Same is the situation on the distribution side, where as more and more consumers start participating in the grid function, their information of the component, information of the devices that they use, that would be available with the system operator, distribution system operator, or the aggregator, and also he would be able to control those components. So that gives an opportunity, that gives a requirement of bidirectional information flow as well. The information flow, obviously, it is through traditional communication channels. It could be in terms of GSM, it could be in terms of the other modes of communication, that we use. So any of those communication modes can be used depending upon whether the different nodes are nearby, whether the network connections are strong. So depending upon the geographical locations, different type of communication infrastructures can be put in place. So essentially, smart grids is about developing those advanced facilities. Obviously, it is not about changing the existing grid, but adding different layers to that grid. So it is not that the network is going to change, but there will be certain components impregnated into that network or on the consumer side. We are not going to change the devices that we are using on the consumer side, but we'll have more monitoring devices, sensors being installed along with them. So it would give more visibility. And we'll continue to use the existing set of infrastructure in existing set of devices that we have got. Obviously, this would require significant investment, but and one of the reasons why it was not done earlier and why it is being done is the cost reduction that has happened over the decades in terms of communication technologies. So the devices that people have started using for communication, they are becoming cheaper and cheaper, and those technologies that were developed earlier for primarily for communication in other sectors are now becoming amenable for communication in power sector as well. So there is a cost involved, but as the value that we derive that improves, the impact of that cost involved, the whatever is the cost involved, that can be recovered sooner than later. What essentially the grids would lead us to, smart grids would lead us to, is that instead of having manual interactions, instead of having the person meter reader going to the physical location, or the person who has to rectify the network going to the physical location, there would be more of self-reporting, more of self-diagnosis, self-healing systems. Reporting would be done automatically through standard communication channels. Instead of having periodic maintenance, smart grids would focus on predictive maintenance. So based upon the condition of the asset of the transformer or the line, it would indicate the need for predictive maintenance rather than going in for a periodic maintenance, which essentially would involve investment on a regular basis, recurring investment on regular basis. Predictive maintenance could be more focused so as to ensure that even if there are more frequent requirements, they can be done. And in case of infrequent requirements, the cost can be avoided. Traditional grid would have more of manual switching. Trouble response has to be handled personally by personal human beings. In case of smarter grids, decision making is not done at the central level. It can be done at the local level. Automatic responses, predictive maintenance, predictive avoidance of any uncomfortable events can be done. So these are the broad benefits that we derive from making the grid smarter. This is something that more or less most of us have come across. The key features that it would offer is moving away from electromechanical systems to digital systems, from one-way communication to two-way communication, rather than having central generation to having more of distributed generation, having few sensors towards shifting towards a scenario where we'll have more and more sensors. Monitoring would become self-monitoring rather than having a manual monitoring of systems. So substations, etc., would have less humans being deployed. Restoration would lead, instead of having manual restoration, we would have self-healing capabilities in the systems. Instead of having failures and blackouts, we expect that the system would become more adaptive. It would it would have its self-healing capabilities, and it would be able to island itself in case of any such uncomfortable situations. The challenge is that it would have more pervasive control by the system operators or by the control room people. Though the benefit is that the customers would be able to access more services, would have wider choices in terms of securing power, in terms of not only in terms of the type of services, but also in terms of the type, the value, the cost that they would have to bear for securing those services. So these key features broadly, I think most of us understand. I've already touched upon this: two-way communication, self-healing capabilities, real-time monitoring control, integration of RE, active customer participation, advanced metering infrastructure that would be deployed in the systems, greater possibility of EV integration, a lot of distributed generation, automation, and intelligent control. This is very generic, what we all have touched upon all these years. The drivers, the things that drive these changes in the grid, they are essentially related to the desire in the human being for more reliable power, having choices in the system. So it empowers the customers. That is one of the things that drives the grid to be made more smarter. Economy of choices. So in order to provide that economic competitiveness, you need to provide that those services at from different stakeholders, so that they'll be able to provide those at a competitive rate. Environmental sustainability, obviously, it is a part and parcel. People are more, I would say, focused on environmental sustainability, and they would be willing to exercise their choices on which sustainable options they would like to secure their energy supplies from. So all these things, they drive the grid to become more and more smarter. The benefits obviously linked to those choices, linked to those drivers, is the benefits that they would drive is in terms of improving the efficiency of the system, both in terms of energy efficiency and in terms of operational efficiency of the system. So these are the benefits that individuals as well as systems would gain. Customers, because of the wide choices, because of the improved reliability, they would be more satisfied with the smarter grids. Environmental benefits would relate to lower emissions. So these are the broad set of benefits that people derive, both the industry as well as the consumers, and the I would say environment as a whole, such that there is a win-win situation for all stakeholders to shift towards a smart grid system. Sorry. Where I'm moving slightly faster initially because I believe the audience is more from the electrical side and they understand some of the basic facts easily vis-a-vis, rather than having a new audience. So some of the challenges, while we talk about smart grid, some of the challenges which have hindered over all these years is obviously one of the reasons is technical requirement. The devices that we use, I've just shown a couple of examples, but there are more examples, more points that we can add on to those. The challenges of transforming the grid is obviously, one is technical requirement. A lot of new technology has to be developed to make the grids smarter. The existing technologies which were there in the system a decade ago, they would not make the grid smart. So impregnating those communication technologies into the power grid, into the grid, or into the distribution system at household level is something that requires development of new technologies. I think those people who are into this system for over 2 decades, they will realize that things have evolved over the last 2 decades in terms of new technologies, new devices, where control and visibility has improved. Market options, they also have evolved over the last 1.5 decades only. So those were earlier a restriction because the grid was vertically integrated and the choices that the customers were having were relatively limited. So because of the lack of incentive, there was a lack of investment, and there was a lack of investment from the investor side, as well as lack of incentive from the customer side, because the tariffs were more or less static. and they did not reflect the true cost of supplying the power. So the customer did not have an incentive to rework or revisit its the current I would say the expenses it was incurring. So there was no incentive for him to participate. Presently, those things are evolving, and as you see what is happening in India as well, the electricity policy, new electricity policy that is coming up, that is likely to bring in more such opportunities for the customers on the distribution side, creating retail markets possibly. Social engagement, obviously, because traditionally there was a limited engagement with the customers. One of the reasons was that the cost of electricity that household would have to bear was still relatively low vis-a-vis its overall budget. So bringing all those customers to participate in the grid function is something that is evolving. People have concerns. Privacy is obviously one concern, but apart from that, there was limited economic benefit also. So as the technology becomes cheaper, the incentive for the customers to participate is evolving, and it obviously starts with those consumers which have got high power consumption, like industries. So individual householders or small consumers are relatively the last one to join this bandwagon. So social engagement obviously would evolve over a period of time. To coming to the core focus of this lecture, to give a broader understanding of smart grids, we need to go back to one of the diagrams that you see on this slide. It was published by NIST, National Institute of Science and Technology in US in 2014. So it's about a decade old. But this does give a broader understanding of where all the changes are likely to happen. So changes are likely to happen on the generation, transmission, distribution side, customer side, operation side, market side, and in terms of development of new service providers. So obviously the interactions earlier, which were limited between the customer and the grid, there was a single point interaction. Now the customer would have a choice to interact with the service provider or the control room or the market or the transmission and distribution grid separately, and at times to the generation as well, depending upon if he has got direct connection with the generation systems as well. Similar to that, the interaction between different nodes would be more, I would say, multinodal interaction rather than having a single flow of interaction. So this is how it was visualized about a decade ago, and we are living to that vision. The interaction between different stakeholders is obviously evolving, as you see in this graph. I'll be touching upon each one of these separately so that we understand what all changes are happening in each vertical. Broadly, to start with, on the customer side, obviously there's lot many things that we can discuss, but to be very brief, on the customer side, depending upon what is the type of profile for a customer, the grid interactions can vary. Broadly, as on date, we do classify them in terms of residential, commercial, or industrial. These are very broad classifications based upon their capacity to pay, as well as based upon the type of activity that they do. It is presumed that the industrial and commercial consumers have got higher paying capacities vis-a-vis residential consumers. So the tariff design is also higher for those consumers and less for residential consumers, though the cost of supplying electricity to the residential consumers is higher vis-a-vis that for the commercial, and obviously for commercial is higher than that for industrial, because industrial consumers are primarily connecting to the grid at higher voltage levels. So we classify them depending upon what type of consumption patterns that they have got. And based upon that, the way by which the grid is to be made smarter varies. So if you want to make it smart grid from a residential consumer perspective. It would be more about, I'll just showcase you. I think if you see from a residential consumer perspective, it would be more about being able to control the appliances. It would be about having a household meter, smart meter at the house, having thermostat at the house, which can measure and control some of the components. Some element of automation has to be brought in. There will be some distributed generation as well. This is primarily the focus of customers, residential customers. These are the things that would evolve in for a smart grid system. If we are talking about commercial spaces or buildings, it could be buildings having campuses which would require more automation. There may be storage facilities. Building automation obviously is a thing that is evolving because of the not only the individual household consumption, but the common consumption happening on the grid side, common consumption happening on the building side. Meters obviously form a part and parcel of it. That is one. And apart from that, also commercial spaces like malls also have to be managed in a similar way. So now you'll see more and more malls having storage facilities in terms of energy storage facilities, having centralized energy management systems, such central cooling systems, which require coordination across all small units within that commercial building. So those type of systems are evolving, and there is a viability also. So more and more focus is towards creating viability through creating storage, creating solar panels or distributed generation on their side, and obviously through more of automation. On the industrial side, the facet is slightly different because there's a lot of motors, a lot of lighting load and motors which need to be controlled. There could be co-generation as well and distributed generation as well. And there could be sub-metered processes as well, in which you would be monitoring what is the consumption of components down the line through sub-metering systems. So these all also are evolving to smarter grids through automation mechanism. The meters are obviously there in the system. So each facet is evolving, making itself more smarter and smarter in terms of how to manage electricity. So each facet is basically essentially what is the focus is. Each type of consumption, each type of consumer has got a different facet to work with. And when one starts understanding smart grid, all those facets have to be dealt with a different thought process. So if you're trying to design a smart energy system for a home, it would be different from that of a building, and that would be different for that for an industrial campus. That is essentially what I would like to focus upon. And obviously, all these would be interacting with the service providers. They would be controlled through operation mechanisms. They would be connected through distribution systems or maybe through transmission systems. And they would have an opportunity to participate in the market, buy and sell in the market, each one of those, depending upon what is the voltage level and what is the level of consumption that these guys have got. What the consumer provides is opportunities to participate. It provides demand response. And when we say demand response, it could be through any one of those. Any one of those could provide demand response, help the system to manage the demand supply balance in terms of peak load shaving or valley filling. So these are the benefits that the customers provide to the grid to make it smart. That is why people are incentivized. There's underlying economics as well as the evolving technology that helps, that makes it the customers participate in these systems. Smart buildings or smart home solutions, obviously on the consumer premises, they provide, I would say, seamless control for the consumer and a happy experience of consuming energy rather than each time having to switch on and off the switches. Those things can be done in a more automatic fashion, and that gives them more control over how they consume energy, different devices, how they consume energy over these devices. Obviously, all this would require investment in terms of communication infrastructure and in terms of creating those markets and new players in the system in terms of system operators at the local level and so on and so forth. If we look at the market side, in order to make the grid smarter, we also need to make the we need to create market opportunities, because until unless there is a value, economic value that the customers get, that is one part, and second, they get the choice. Their interest in participating in the system would be relatively restricted. So while we are trying to design smart grids, markets is an inevitable change that has to be done. Markets need to be developed, keeping an understanding that the customers, different type of customers would like to communicate through the smart grid, and then only they can participate in the market. And that is where the value as a consumer they would get. But while they are participating in the market, the regulators, the governments also have to focus upon developing appropriate mechanisms, appropriate regulatory policies, appropriate technical regulations, such that they do not disturb the grid operation. Their participation only because individual participations can at times it can be slightly disturbing as well. Presently, where we see a limited number of limited regulation, technical regulation, if everybody is putting up a solar rooftop, it is quite likely that during the afternoon hours, the net demand over the grid would significantly reduce. And that is where we are presently heading towards. So we need to have appropriate technical regulations, appropriate economic regulations, such that whatever market participation is happening from the customer side, that is for the benefit of the grid, that is for the benefit of managing the grid, rather than only for the benefit of the consumer. And all this obviously requires all that information, pricing information, to be made available online so that appropriate decision making can be done. As far as the issues of service providers are concerned, we need to obviously provide new service providers, because the traditional service providers in the industry, they do not, they cannot obviously create opportunities for the customers. So in order to create those opportunities, you need to have new market participants like retailers, aggregators, which differentiate the services from conventional distribution network licensees, provide customers with different choices in terms of money and in terms of quality and in terms of the type of power that they want to consume, in terms of the reliability of the power. Obviously, when you are creating such service providers, you need to create appropriate communication infrastructure as well. So all these facets are essentially interrelated. So you cannot have a simply making the grid smarter without making economic value for either the grid or the consumer. And for making that economic value, you need to restructure that grid. And for eventually that restructuring leads to new market designs, and new market designs would eventually lead to creation of new market players. So all these facets are essentially they are interrelated with each other. That these only would give opportunities for to the consumers, like having more renewables, they managing their customer complaints in a more seamless way, in which they need not call each time there is a fault in the household. The company, the retailer would automatically know that there is a fault. The response would be automatic, and auto restoration, auto healing would be there in the system. That is what the consumer, present day consumer and the future consumer would like to have. And that obviously has to come through overall evolution of things in terms of technology, in terms of markets, in terms of industry restructuring, and in terms of consumer participation. From the grid operation perspective, this is another facet of the system in which the grid operator would require to communicate, because eventually it is the one who has to ensure that the grid operates reliability, that at least the superstructure of the grid, the overarching grid, that operates reliably. So the grid operator also wants more and more visibility into the system, so that it can actively monitor, it can record, analyze, and control the operation of different components in the system. Real-time information exchange is required for the grid operator to take a decision. It also needs to understand and interact with the market side. These operators, obviously, because there are a lot of service providers now, retailers, aggregators, ancillary service providers, market operators, so many new nodes with whom they have to interact. So communication becomes an integral part of all this operation, and information exchange with all stakeholders becomes critical for providing any new change, whether it is demand response on the consumer side or whether it is grid management on the grid side. Any such thing, it will require enhanced focus from the grid operator. So as a grid operator, it would like to monitor, it would like to analyze the faults, it would like to control the components, it would do its on a load control on a regular basis, it would report the statistics, it would analyze those so as to understand where are the weaknesses, where new investments are required. So all these are actively being done by network operators. As a grid perspective, you will see planning and operation that is more now, because of the significant quantum of information being made available. The planning and operation decision makings are done in they are done in a more I would say systematic way, with more informed decision making is done. Maintenance and construction of the systems is also it is becoming more systematic in terms of planning. If you talk in terms of planning, whenever presently we are planning any new generation facilities, we are obviously being able to plan the network beforehand so that network congestion does not arise. Obviously, all these are an integral part of the planning and control mechanisms in the system. As far as the generation domain is concerned, because now the scenario is significantly changing. Earlier, there were only large power plants, and those power plants had to be operated. They were more controllable. They were the control. They were, I would say, the generation from those power plants were more controllable. The challenges for the grid operator were relatively limited. In the present day scenario, where significant distributed generation, RE generation is coming up, the grid operation is becoming more challenging, and it has to focus upon, the grid operator has to focus upon, more focus upon the conventional power plants, such that whatever RE penetration is happening in the system, it is able to mitigate, it is able to operate the rest of the system plants, and also bring other type of sources like biogas and pump storage, such that whatever are the variations happening on this side are being managed by conventional are being managed either by the conventional power plants or through new generation technologies. And obviously all this requires a lot of information flow between those power plants and the system. Transmission system, again, that is another facet that needs to be focused upon. In transmission systems, when the present day focus is to have, rather than operating those substations from physical locations, more and more focus is to operate those systems from faraway locations so that human intervention is reduced. Fault locations, fault management is done from remote locations. So all this requires a lot of communication infrastructure to be installed from those substations to the central operating stations. Monitoring of those lines has becoming, over a period of time, it is becoming more and more, I would say, granular. It is the monitoring in terms of monitoring the voltage, frequencies in the system, power flows in the system, that is becoming more and more focused, which eventually leads to investments in terms of putting up those smart meters, putting up PMUs at different points in the system. All these provide a seamless information to the system operator who would try to minimize the cost and maximize the utilization of the system, improving thereby the reliability in the grid. On the distribution side as well, the benefits, the changes that are happening in the grid are similar. However, because of significant investments happening, or significant generation happening on the distribution side, the distribution side has to be significantly revamped in terms of strengthening the grid, in terms of allowing reverse power flows, in terms of promoting distributed generation so that localized but uncontrollable RE generation the impact of that can be handled at the local level itself, and it does not impact the grid as such. And this is where new evolutions like peer-to-peer markets, distribution system operators, they are coming up, primarily because they see an opportunity to manage the grid at the local level rather than allowing those generation to impact the higher voltage levels in the system. There's a lot more that we can discuss, though there are time constraints, I understand. But just to touch upon the broader facets, when we see all those facets of smart grids, we need to separate out all those functionalities in terms of, I would say, generation, the voltage level, the type of systems that exist from the power side. That is about, we need to separate out what is generation, what is transmission, distribution, distributed energy sources, customer premises, etc. And from the zonal perspective, we need to focus upon what are the processes involved, what are the fields that we need to focus, stations, operation, enterprise, and eventually the markets. From broader perspective, we need to separate out the component layer, the different components of generation, transmission, distribution, from the communication layers, which essentially are to be superimposed over the components. Then upon those, we need to have information layer which connects these components over the communication layer, so that what information is to be captured from these nodes, this node, this node, and eventually has to be processed over the function layer, creating specific use cases, making a business layer, which obviously is markets, where the value of all this investment, the value of creating all this investment would be visualized. I think in the interest of time, I'd like to stop here, and if there are any questions, I'll be happy to answer those. Though there's a lot more that we can discuss in this segment, but I think we will stop at this point as of now. Any quick questions? Any other participants got any questions? Kush, I hope I'm audible.
Yes, sir, you are audible, sir.
Okay. So if there are any questions, I'll take up those, else I'll take a break of 2 minutes and then we'll come back to the session again with a new class. I think there is a question which I would be happy to answer. Just let me check how to. There are slight challenges in how I operate my. I'm still to figure out how to stop sharing. Just hold on for a second. Are you able to see my presentation or are you able to see the whole screen?
Sir, whole screen we are able to see.
Okay, I'm just trying to figure out because this is now minimize this slide. Okay, let me see. Focus. Never mind. I'll try to answer a couple of questions. Kush, can you just check what are the questions in the chat box? I'll try to answer those.
Yes, sir. Sir, question at 12.1. How pricing can handle congestion issue?
How pricing can handle congestion issue? Common question, simple question is similar to how we handle it in other networks. Like in the case of travel bookings that we make, cab bookings that we make, Ola and Uber. We practically come across situations on a daily basis when we want to book a cab during the evening hours or during a festival. The number of cabs available on the road are relatively low, and the number of people who want to travel are relatively high. That leads to a demand supply imbalance, leading thereby, or maybe there may be a lot of traffic because of some event which may lead to congestion on the road. In those cases, effectively, when we try to book a cab, the prices for Ola, Uber, they would significantly increase vis-a-vis what would be the prices um, otherwise in a normal situation. So they lead us to a situation where those people who would see the higher prices, they would tend not to travel and thereby lead to a reduction in the demand in the system, thereby leading to a balance between the demand and supply in the system. And if the demand still increases, the prices for using the network, the prices for booking the cab, that increases. In a similar way, as if we start having more and more smart grid penetration, smart meter penetration into the system, that would eventually lead to customer participation, customers being able to see what are the prices, and based upon the price values, they'll be able to respond when to use electricity and when not to use electricity. Possibly during the evening hours when the use of electricity increases and the supply is not available so easily, in those cases, obviously the demand would change accordingly, thereby helping the grid to balance itself. In a similar way for other situations as well. Next question, Kush.
Next question is, why do we focus more on energy efficiency rather than the demand side management in Indian context?
Energy, there is a simple reason for that. People focus more on energy efficiency because those solutions are easy to implement from a higher level from the government perspective, like the changes in manufacturing the devices that we use. Those are easy to implement, and those are essentially related to the replacement of components that we use. So if the manufacturing can be controlled, if we are able to control the manufacturing of inefficient lighting devices, inefficient fans, inefficient motors, eventually the choices that are left with the customers would be limited, and they would have to shift towards more energy efficient systems. That is easy to do. Yes, doing demand response is slightly difficult for the reason that demand response would entail providing more meters on the demand side, which would entail significant cost and on the customer side, and the value that the customer derives by making that investment is relatively low vis-a-vis the value it would have without doing those interventions. So the incentive for the customer are relatively low. In the case of energy efficiency, significant cost is being borne by the government in terms of by way of subsidy. That is why focus on energy efficiency is more vis-a-vis providing demand response mechanisms. That is essentially the reason. The moment the cost of electricity becomes higher and the value that they derive, the benefit that the customers would derive from demand response increases, then obviously, and then in that point of time, obviously, the customers would start opting for demand response options on a wider scale. Next question.
Yes, sir. The next question is from Satyanarayana.
Yeah.
How to develop our Indian smart grid pilot project, where we can see reports on their operation and improvements.
The ports, I think a lot of pilots have evolved over the last 5 to 10 years. Obviously, it requires investment in communication, and these cannot be done at individual levels until unless you have got access to the consumption. And that access can either be if the government is not providing, the network operator is not providing that access over the distribution network, then the access can only be provided at the household level by willing consumers. So possibly you could develop an app which monitors and controls and observes the power consumption of individual devices for those willing consumers. That could be one of the ways, but then to enable them to adapt or use that application, you'll have to create some economic incentive in terms of maybe reduce bill. Something of that sort has to be done to enable them to use those smart grid applications. Rest, as far as investment in terms of communication is done, that obviously is beyond the scope of individual users. That lies more with the I would say the grid operators, the network operators, and so on. Next question.
That's all we have, sir.
So I hope I've answered all the questions.
Yes, sir.
Okay. So give me a break for 2 minutes, and I'll join thereafter again. Give me just a break of 2 minutes.
Sure, sir.
Second session on demand response, demand side management. Kush, hope the slides are visible.
Yes, sir. Visible, sir.
Okay. Again, because most of you come from electrical background, I'll prefer to skip the initial portions, which most of you are aware about. Demand side management, more or less, we do have a basic understanding, so I'll skip the initial slides, but not the basic thought process. The key challenge that we are facing in the industry is specifically in terms of Indian industry is there's a significant peak demand deficit of power. Essentially, we have got about 500 gigawatt of installed capacities, but the peak demand is still somewhere around 250 gigawatts. So that reflects very badly that eventually, despite having made investments of about 500 gigawatt, the eventual utilization, peak utilization or peak demand that we can fulfill is limited only to 250 gigawatts. That there are several reasons for that. One of those is limited network capacities. One of those is limited availability of those power plants at the same point of time. And another challenge that we are facing right now is energy transition in terms of shifting from conventional power plants to renewables, which do not provide power at all points of time, thereby limiting the ability of the grid to provide the required generation at all points of time. These are the broader challenges that we are facing. We are evolving. Will be more connected. Will be more interconnected in a sense. More digitization, more smart meters, more Internet of Things will be more distributed in terms of generation. The opportunity coming from higher RE penetration will become more efficient in terms of utilization, as we have just discussed. Not only component efficiencies, but system level efficiencies are also evolving. Will become more electric in terms of the demand diversification, in terms of the energy diversification. Our consumption of the form of energy that we use, it will be more and more electric. So we'll be using more electricity as a part of our overall energy consumption portfolio. These are the changes that are happening at the higher levels. The structure of the grid is also evolving. Earlier, it was more control and dispatchable generators. Now there are more and more uncontrollable generation. However, uncontrollable let me focus. Earlier, there was more and more controllable generation. We are now having more and more RE-based uncontrollable generation. Earlier, the demand was non-controllable. Now the demand is becoming more and more controllable because there are several components which are now easy to manage. So we are shifting from a power system in which there was a conventional generation. The generation was controllable, which was essentially handling a system demand, which was non-controllable. And the generation was following the demand in a way that it would always, the generation would always vary itself corresponding to what the demand is. We are shifting towards a scenario where the generation is becoming uncontrollable. So its ability to follow the demand reduces, thereby requiring us to focus upon providing that required flexibility in the system from the demand side, either from the demand side or through energy storage. So the focus is on having controllable demand, flexible resources, and having that one of the facets through which it will be attained is by having more and more energy storage on the distribution side. This is how the grids are evolving. Why do we need to focus upon demand side management, demand responses, and demand side management? Is because we cannot continue with that investment of 500 gigawatts and more, and also on the transmission network, we cannot continue, despite that we understand that the quantum of peak demand that we are fulfilling, and corresponding to that, the energy demand that we are fulfilling is also limited. So that leads us to a situation where we need to focus to balance the demand in such a way, to normalize the demand in such a way, such that it is aligned with the generation. It is aligned with the generation rather than the generation getting aligned with the demand. So this is the fundamental change in the grid, which is leading us to focus more on the demand side management. Because if you do not manage the demand, then in that case, handling the grid with an inflexible RE generation would become significantly difficult. So this focus on demand side management, which will solve the issues plus allow us to continue integrating more renewables into the system. The definitions, you can check various sources. Everybody has got a different definition. But broadly speaking, it is a portfolio of measures to improve the energy systems at the side of the consumption, on the consumer side. So whatever changes, behavioral changes we want to make on the consumer side to manage the demand comes under the domain of demand side management. The understanding that commonly people have got and what actually is, will slightly focus on that. I've just touched upon that on the supply side. When we talk about supply side management, it is essentially we are focusing on the generation and transmission systems. The distribution network actions, they do not, they like distribution loss control, load shedding, use of RE, they do not come under the domain of demand side management. However, the end use side actions like curtailing the uses hours, using efficient devices, using solar devices, and shifting the load, they come under the provisions, they can come under the scope of demand side management, which essentially is being activities that are being done by the consumers to mitigate the load on the system. DSM classification, demand response obviously is one part of the demand side management scenario. Energy efficiency is another part. The question that we just discussed, why energy efficiency, people are focusing more on that vis-a-vis demand response. Energy efficiency is easy to bring in through subsidization, components can be replaced. Demand response eventually depends upon consumer behavior. That is the next step that we need to focus upon. We need to create scenarios, create use cases by which the value for the customers is there. Essentially, when we use energy efficiency measures, that leads to a permanent reduction in the consumption across the load curve. So the red curve vis-a-vis the black curve is the change that you see when we make the devices energy efficient. Whereas when we talk about demand response, the demand response, these dotted lines, they indicate the demand response. That is about leveling the demand curve, reducing the peak demands, filling the valley demand, such that the demand becomes more or less uniform, and which is easy for the generators to supply. Demand response obviously leads to reduction of overall system peak load as end users shift their operation to some of their loads from peak hours to off-peak hours. Majority of the demand response programs are designed to enhance reliability of the system. So their aim is to improve the reliability of the system and to reduce the energy production from fossil fuel-based power plants. Some of these graphs, some of these pictorial representations, you would have seen one from different books at different points of time. Specifically, it is classified. I've just classified those thoughts. So there, when we talk about demand side management strategies, we talk about energy consumption, energy conservation, which reduces the overall energy demand. We talk about peak clipping, which reduces the peak in the system. We talk about load shifting, in which we shift the load from peak hours to off-peak hours. We talk about flexible reliability, in which we induce a change in the load as per supply. So the load evolves as per the supply availability. We talk about strategic load growth, That is why we promote those components with devices which would require electricity. So, and utilizing that at appropriate times. We talk about valley filling, in which the focus is on increasing the load during off-peak hours. So these are some of the strategies that we adopt while focusing on demand side management. The four verticals of demand side services to the grid, they talk about changing the shape of the load curve. They talk about shifting the load curve. They talk about shedding the load. They talk about shimming the load. So these are four sets. When if you specifically want to see the definitions, changes in the consumer behavior that would lead to the changing the shape of the demand, shifting the load without any net reduction in energy consumption. That comes now. We also need to understand that changing the consumer behavior is a long-term phenomena. It is not a daily phenomena. The impact is long-term, whereas shifting the demand is a relatively short-term phenomena, and it does not change the overall energy consumption. It only shifts the energy demand. Load shedding is even a slightly less short-term phenomena, in which we go in for shedding the load to reduce the demand at the time of peak demand or when there is a system emergency by load curtailment of end users. Shimming the demand response that is linked to the flexibility, that is the ability of the load to dynamically adjust the demand. Those type of demand response is presently only for short-term grid support services, short-term in terms of hours, minutes, and seconds and milliseconds, primarily to provide those short-term grid operational services like inertial response or frequency responses in the system. So depending upon different time scales, different type of demand services, demand response services or demand side management services provide different services at different time scales. And depending upon what is the grid requirement at any given point of time, are we looking into a long-term planning perspective? We'll focus upon shaping the demand. If we are talking about a relatively shorter term time frame, we'll be talking about shifting or shedding the demand. And for very short term grid services, we talk about shimming the demand. So this is how we classify the cases of demand side management. In order to provide demand response, the essential part is to identify who would be the stakeholders in providing that demand response, whether the stakeholders are utilities, load aggregators, or the customers, or an integrated model by which these three players they participate. Obviously, demand response provides technical readiness in terms of having more smart grids in a sense. Technologies would enable those demand response programs because through technology, through hardware, through software, and through communication, transfer of information and transfer of decision making can be done. Stakeholders presently, if you see focusing utilities would essentially require demand response so that they can manage the grid. They would be they'll be triggering the demand response events. That is, triggering would mean they would let the stakeholders like the aggregators or the consumers know when to provide the demand response. The utilities would be the one who will be making the payments to the consumers. Utilities would be the ones who would be doing the forecasting and grid planning through data analytics. As far as the role of load aggregators is concerned, it would aggregate the load. It would be a communication between utilities and the consumers. It would decide the penalties. It would face the penalties if it is not able to provide those demand responses. Customers are the key component of providing demand response. So identifying those customers and their participation in the demand response program willingly, being in terms of energy efficiency measures or in terms of short-term demand responses. Their willingness is key to providing demand response, and based upon their interest, based upon their behavior, would the demand response programs evolve. As far as the role of regulator is concerned, regulators are supposed to facilitate creating appropriate demand response programs, creating mechanisms by which the utilities could offer demand response programs, and ensuring that the customers benefit from those demand response programs well in time, in terms of returns, in terms of bills, managed bills. Eventually, the regulator has to see that all those demand response programs are not only for the benefit of the utilities, but they also align with the broader energy and environmental goals of the industry. Candidates for demand response would include residential demand response candidates. These could be controllable appliances in your house, washing machines, etc. Air cooling systems, HVAC systems, lighting could be a candidate for demand response, refrigeration, cooling demand, washing machines, cloth dryers, hot water heating system. These are devices, these are components whose energy consumption, the time at which energy consumption happens, that can be varied. So that creates opportunities to provide demand response from those candidates, from those devices. As far as commercial consumers are concerned, cooling demand, lighting demand, heating demand, and pumping demand, these are the demands which can be made flexible in terms of their time utilization. So they are amenable to providing demand response. Similarly, for industrial consumers, cooling, lighting, cold storage could be one of the segments. Backup generators and operational process, managing those operational processes could be the facets through which the demand response programs can be activated. This is a broader classification of demand response programs. Demand response programs could either be price-based or incentive-based. When we talk about price-based programs, they could be real-time pricing, time of use pricing, critical peak pricing. These, along with these, the direct load control and emergency demand response programs, they form a part of voluntary programs, though DLC and EDRP are incentive-based programs. Apart from those, capacity markets and curtailable services, these could be mandatory programs being run by the system operator. They could be incentive-based, but they could be made mandatory. Apart from those, the other incentive-based programs could be demand bidding or ancillary services market, which primarily are done through market-based algorithms, market-based programs, in which people would participate, and the system operator would require those services, and people, stakeholders, whether it is retailers, aggregators, or consumers, they participate in the demand response programs by utilizing the incentives that the utilities are providing in the system. So this is broadly how we classify the demand response programs. If we talk about price-based programs, obviously the customer, depending on the type of customer and depending upon the type of uses that you want to change, you could adopt one or more of these real-time pricing, time of use pricing, or critical peak pricing, depending upon how much control you want to keep and what is the focus. If it is only about managing the critical peak in the system, you could adopt critical peak pricing mechanisms. If you do not have, if you just want to manage the load curve, possibly you could use time of use tariff designs, which would help mitigate the demand during peak demand hours. Real-time pricing is essentially focused upon large consumers, wherein the consumption during peak hours could be mitigated seamlessly through real-time metering systems. When we talk about real-time metering systems, the granularity could be as low as 15 minutes or 5 minutes, depending upon the size of the consumer and obviously the metering mechanisms, underlying metering mechanisms. Um, Time of use pricing, we all understand, but I'm just reiterating those. It is a tariff that applies to use of electricity over scheduling of periods, where the price is fixed by the utility company for each period. Essentially, it leads to scenarios. It leads to situations. It leads to opportunities to shift the demand over a longer period of time for a couple of hours. So let's say if you want to shift the peak demand, evening peak demand, you would use a time of use tariff. So you divide the day's demand into different scenarios, peak, off peak, or on mid peak, and so on. And peak hour tariff design is there to increase the peak hour tariff is higher vis-a-vis off peak hour, so that the shifting of demand is made possible. Critical peak pricing, it is different from time of use pricing. For emergency periods, critical peak pricing modules are adopted. Charges for those periods are much higher in emergency periods when the prices remain the same while the prices they remain the same for other periods. Real-time pricing is a more dynamic pricing setup, which reflects the real-time prices based upon the current supply and demand conditions. These prices differ interpretably in response to the wholesale market prices. So essentially, in real-time pricing, there would not be any control over the prices. They would simply reflect what are the wholesale market prices, specifically focused on large consumers, wherein those would be able to respond to those price signals on a real-time basis, because eventually the consumption of a small consumer is relatively less costly. So for a small consumer to participate in the market and respond to real-time signals is not an economically viable show. Incentive-based programs could be in terms of creating rebates for the consumers for reducing their electricity usage during specified periods, or making them payments to achieve specific energy reduction targets. Non-financial incentives could be in terms of creating rewards or recognition in terms of to value the benefits that they are providing to the grid. So apart from economic incentive, also there could be non-economic incentives that can be provided to the grid, that can be provided to the customers for them to participate in demand side management programs. There could be voluntary programs in terms of making your components available for direct load control, in which customers allow some of the components to be remotely controlled by the utilities, specifically large energy consumption devices, so that the utility may control whenever there is insufficient supply of electricity or power in the grid. Emergency demand response programs, they are equal to the load shedding, in which vis-a-vis load shedding, there would be incentives be made available to consumers to participate voluntarily in load shedding during reliability triggered events. Capacity market based programs. Capacity market based programs essentially, in those customers, they oblige themselves to provide pre-specified load shedding whenever there are contingencies in the system. So for those consumers who are willing to offer load shedding into the system whenever there are contingencies in the system, they help if there are such customers available and there's a market available for them to participate, capacity markets can well be conceptualized in some of the countries. Capacity markets, they are there, like in US markets, the capacity markets do exist, in which the customers, large industrial consumers, they offer themselves for pre-specified load shedding. Other curtailable services, other services mandatory programs could include interruptible or curtailable services, in which customers join to adjust or shed their loads based upon some discounts or some tariff plans being offered by the service industry, by the suppliers. So depending upon what type of programs entities are participating in, you could classify the demand side management programs into different verticals. There could be market-based programs in which you could have appropriate markets. There would be aggregators who would be willing to buy back the demand or essentially reflect that reduction in the demand at certain points of time. Large consumers may like to benefit from those. These are operated through markets and not directly done by the system of the distribution system supplier. Ancillary services market are in which apart from PAPI, apart from the other services, they may be supported by through the market mechanisms like operating reserves, maintaining reserves. In such services, not only consumers but other stakeholders like energy storage suppliers or maybe even general ancillary services programs. We classify the demand response automation in terms of whether the mechanisms are manual or behavioral, whether they are automatic or semi-automatic. So depending upon that, we could also classify. And obviously, depending upon that, the consumers would take to respond to signals would vary. So manual response would obviously take time. It may not always be effective. Automatic and semi-automatic are relatively more reliable mechanisms of providing demand response. Obviously, demand response programs would require great communication infrastructure to be installed, and all that has to be done through the evolving EMI systems that are being implemented. There would be a lot of communication infrastructure that would be required in providing the residential demand response programs. This is just a glimpse of such demand response program, in which you can see focusing on the wide area network, home area network, and so forth. So at various levels, we could develop those communication infrastructure to provide the system responses, either at the home area level, the wide area level, or at the aggregator level. This is just a glimpse of the same thought process. The type of this is just to give an understanding of the type of infections that can happen. You could have daily energy efficiency measures, which have long-term measures, time of use, time of day tariff, which are still slightly short-term. Daily peak load management, day-ahead demand response, real-time demand response, and spinning reserve. So as you as you go up the scale of this pyramid, those are fast responding devices. Those are systems demand response programs which operate at a shorter time interval for which basically operate in the grid with the signals being received in a very short term time frame. They would require, obviously, because of that, they'll require increased level of control and speed in the system. Who would do the aggregation? It could be the discoms can operate as sole aggregators. Discoms can act as mega aggregators for those, or you could adopt a hybrid model as well. So essentially, either the discom retailers could act as aggregators for providing demand response, and as an aggregator, they would be aggregating the responses from various stakeholders, various consumers in the grid. This is just a schematic diagram which we got from one of the utilities in Delhi, how they are adopting demand response programs. Just a similar detail from the same utility. This could be a system level visibility to create a demand side program in which essentially we do a load research and market potential assessment for specific type of demand response. We do some planning, we design a program based upon that. We implement a program and we assess the program for its effectiveness. This is how usually demand side management programs are conceptualized. Some of the states in India, they have already adopted advanced demand side programs. Some of the states are relatively slow in adopting those, so that varies from state to state. This is just a glimpse of those states which have already adopted time of day tariff, which was easy to adopt. And when we use the term time of day segments, it is not for all segments. So if you see the green ones, it is only for the industrial and consumer segments demand time of day tariff. This color indicates only for industrial, while some of the states they've already adopted it for industrial consumer as well as residential consumers. So there are the various pilot projects that have been adopted, that have been deployed and showcased in different by different utilities. So there are a couple of those over the last decade. I'm not going into the detail. More or less, they've got experimented with different type of demand response strategies to assess. The aim was to assess different type of demand mechanism. And that is across the world. So the advanced mechanism, some of the advanced markets like Australian markets, they have adopted incentive-based participation also. So on and so forth. Virtual power plants, again, these also have been experimented with. This is I think the first focus of the presentation. I'll just touch upon few more things. If there are any quick questions, Kush, I'll be happy to take up those. Else I'll touch DRO as well.
No questions
If there are
available.
any questions, pardon?
No question available, sir.
Okay. So essentially, though we understand that demand response has to be provided by, it is necessitated in the grid. However, we also understand that it is not coming up in a big way. So one of the solutions is to make demand response obligatory in terms of regulation. So when we mean making it obligatory, that means essentially we set up certain standards, set up certain regulations that that forces the utilities that stakeholders to provide demand response. So this is a thought that we have developed similar to renewable purchase obligations that are being done by the utilities, in which they are forced to purchase a certain level of generating capacities from renewable generation. In a similar way, it is being proposed that you could obligate the utilities to provide demand response. And when you obligate the utilities to provide demand response, that would essentially reflect that at least maybe we can say 1%, 5%, or 10% of the should be responding to economic signals, should be responding to certain tariff. So in order to do that, you need to create an obligation mechanism and a regulatory mechanism to get implemented. Presently, obviously, because of technology limitations, economics, because of lack of appropriate regulatory mechanisms and lack of coordination, demand response is not evolving in a big way in most of the parts of the world. So a concept similar to RPOs, renewable purchase obligations, in which people were getting renewable energy certificates. Similar to that, we propose that there could be a demand response obligations as well, in which they get a demand response certificate. And these demand response essentially obligate the utilities to have a certain level of demand response being provided. If we go point by point, assessing the mechanism could be in a way in which we assess the current demand response deployment from different demand response sources as a percentage of total energy capacity, examine what is the historical growth of demand response, identify the drivers behind the growth, and enact policies that can catalyze the trends, analyze whether the identified potential can meet the set targets, progressively increase the demand response obligation targets to align with the national objectives. This is how you push the utilities to provide more and more demand response, identify the challenges being faced by the obligated entities to provide those demand response, to fulfill those demand response targets, and designing appropriate incentive frameworks to ensure that there is a compliance, establishing a monitoring mechanism. The similar way as we understand the RPOs work, and that has to be, the demand response targets have to be set. The retailers or the distribution companies are obligated to fulfill those demand response targets. They issue those demand response certificates have to be issued by the system operator or the market operator. Aggregators have to ensure that they get that demand response through flexible load or demand response programs through from the consumers, and provide those demand response to the grid. And the grid is obligated to fulfill if there is not sufficient demand response available in the grid, the utility, the distribution company would provide more and more incentive, such that this utility does not lead to, this distribution company does not lead to excessive demand. The demand in the geographic area does not lead to excessive demand supply imbalance in that specific area, in that specific geographical licensee area. That is how you push the utility to provide. Any utility is getting excessive, the regulator can ask the utility to increase the incentive, financial incentive for those demand response providers, such that they themselves provide certain level of demand response into the system. And that can be done through targeting, through providing targets to the demand, targets or obligations for the utility to provide those demand response in the system. So essentially, this is just a framework to for the utilities to provide demand responses from their secure demand responses from their consumers. Obviously, in a similar way as we do for renewable purchase obligations, there would be a certification mechanism and tracking who actually are providing demand response and who are not providing those demand responses. Aggregators or large scale consumers, they would get accredited, or they would be the ones who would define whether the demand response is actually being provided or not. I've just added a few more slides on that. Smart meter, obviously, they'll be an integral part of providing this demand response. And without those, providing the demand response mechanisms would be slightly difficult. I'll not go deep into it. I think we're already towards the end of the session. And if there are any questions, I'll be happy to answer those. Any questions?
If there is any questions, you can please type the questions in chat box, or you can raise your hand so we can unmute you. So one question we have from Dr.
Yeah.
From where to buy DR certificates?
This is just a concept that we have proposed. Where do we buy RPO certificates? RPO certificates are, there are agencies which would certify renewable purchases. These could be system operators, or these could be other agencies which are accredited agencies for providing. In a similar way, demand response accredited agencies which do this activity. We'll have to create certain agencies which would certify whether is really providing demand response or not. In a way similar to that we do for RPOs. Any further questions? I think customer, the attendee audience is low, and if there are anybody, Ashish, Bhavani, Umesh, Man, Lakshmi, Rana, Sathi Narayan, Vansh, Viren, anybody, if there are any questions, I'll be happy to answer those on demand side management. Anything on this? Kush, if there are no further questions, we could well wind up the session.
Yes, absolutely, sir.
Thank you all for participating in the session. I think thank you, Kush, for coordinating.
Thank
I
you so
think
much, sir.
we'll meet again in one of the sessions during the day. Thank you, everyone.
Thank you, sir.